And
He's
the
saying about,
invitation kind of came out at the last minute. I got it because I was watching for it.
Yeah. Lately, I've been creating the events lastminute.com.
Yeah.
Like, it's like I took like one extra day to upload James's lecture. I almost forgot about it. Instead of uploading it on Monday, I uploaded it on Tuesday.
Okay. But since the slides end up and the videos end up online, it's all good.
Yeah. Okay. Maybe we can just start the intro stuff. Maybe by the time we get to the main thing, more people will join. Okay, so yeah, so welcome to session 18. Well done to everybody online right now and the ones watching on YouTube later. Well done for sticking with me this long. And we are about to finish. So we are in session 18 of planned session 20, planned 20 sessions. I'm not sure if we should add an extra session. We'll see how it goes, but I think we should be able to wrap up the this crash course by lecture 20. Even though I want to give a little bit of a flavor about the representation theory, I think we should be able to do it, because obviously in the next session, in the next course, I mean, in this here, you will pick up the representation theory in the context of the Lie groups. So yeah, so it's not a big deal if we don't dive too much into representation theory, just a little bit for you to have a flavor. Yeah. Okay, so we are here in the yellow bit here. So we started with the matrix groups in the last session, in particular with the real case. So we started with the general linear group over the reals. And today we'll cover these guys, the orthogonal group and the special orthogonal group. And in the next session, we will switch into the general linear group over the complex field. And then obviously we will then cover the unitary group and the special unitary group. So yeah, so we are getting there. Let me check the chat just to see if there are more people coming in. The regulars, I only see two people, Dimitri and Berend, but that's fine. We can just crack on. So before we start with the new content, just warm up. I know we went through this in the last session, which is this theorem here that says, the group of all invertible linear maps from Rn to Rn, where Rn is understood to be, the real n-dimensional vector space over the reals, is isomorphic to this other group, the general linear group over R. So that essentially means that if you want to do any constructions or computations with the invertible linear maps, you can just use matrices, right? We know how to do that. You fix a basis, for instance, and then you can convert your abstract linear map into a concrete matrix representation. And another thing I think some of you notice is that this construction, this isomorphism, is not canonical. It's not like unique in a sense. So it depends. The construction of this isomorphism depends on your choice of basis. So if you pick the canonical basis of Rn, obviously you will construct one type of isomorphism. It's still isomorphism, but if you pick another basis, you will construct another isomorphism. So it really depends, on your proof. That's why in here I was saying, I hint, choose the canonical basis to construct the proof, because you need to show that these two groups are isomorphic. So that means you need to, build an isomorphism. So the way to do it is obviously you pick the canonical basis and you construct a linear map that satisfies, a homomorphism, a group homomorphism, that satisfies the definition of isomorphism. Okay, and another thing, this is just a side note. I'm just giving a hint here to what's coming in the next course, so you know, as a motivation also for you to to go and review the differential geometry stuff, topology and differential geometry stuff. So this is a Lie group. More precisely, it's a non-compact Lie group, non-compact in the manifold in the manifold sense, right? This is an abstract group theory, but compactness and non-compactness, these are like topological notions. So we won't touch that here, but just to let you know, just to make you aware of this, and also it's a way of you seeing the connection between this abstract group theory and what's coming up in the Lie groups. And it has dimension n square. You will learn why this is the case in the next session. Obviously, we won't do that here in the next not the next session, in the next course. The first challenge I have for you is this proposition. So I have a lot of propositions. Be ready for it. So the set of all elements of the general linear group whose determinant is positive. The claim is that this is a group. So this is the claim. This is a group. So the proposition is as a challenge for you to try to prove. And then the challenge, the other challenge. So this is that's a proposition. It's also a challenge. But then I have another two challenges. Whether this group GL plus of NR is a normal subgroup of the general linear group itself. So what? This is where you need to revise again what we went through in the abstract. The abstract definition of what a normal subgroup is. So the claim is that the challenge. The challenge is whether this is the question is whether this is a normal subgroup. Yeah. And then the second challenge is, okay, so this guy here, this is the set of all invertible matrices with determinant being positive. What about the opposite? The ones with the determinant negative, So the question is whether this is also a subgroup of the general linear group. And if that's the case, if it is a normal subgroup of the general linear group as well. So this is the second challenge. You will see actually this in the Lie group module. These two are actually very, very interesting in respect to the Lie group, to the general linear group. You will see in terms of the composition. It doesn't matter for now. Yeah. Okay. And now we go to the next important matrix group, which is the real special linear group. Here, obviously, I'm using real in the sense of the mathematical sense of the real numbers, not in the human sense of being real or fake. So this set is defined to be the set of all the elements, the matrices in the general linear group, with the determinant being 1. So the proposition is that this is a subgroup of the general linear group. Okay. I guess I could ask, is this a normal subgroup? You can try to answer this. There might even be an answer somewhere. I thought I put it somewhere. Yeah. So that's the first proposition. So this is known as the special linear group. This is essentially obviously this is an abstract algebra course, but geometrically you can view this as the group of linear maps that preserve the volume and orientation on Rn. So this is essentially what the elements of this thing do on Rn. And on a side note, this is also a Lie group. that's why, you know, we went through the we are doing this matrix groups, because they are like natural, they are like a canonical examples of Lie groups. In fact, that's why they are called classical Lie groups. Yeah. So, and the difference is this is, whereas the other one was this is non-compact for n greater to 1. So for the n equals 1, this is compact. That's a claim anyway. You will learn to prove or disapprove this once we get into Lie group section. And the dimension as a manifold, the thing is this, the dimension of this the special linear group is n squared minus 1. You will also in the next course learn how to calculate how come this is a dimension of this Lie group. Okay. And here's another proposition. That's why I said I have a lot of propositions today. Consider R star to be the multiplicative group of the non-zero real numbers, and consider the determinant map. So this map takes a matrix on the general linear group and maps it to the multiplicative group by taking the determinant. Remember, these guys have non-zero determinant, so obviously it will lie in anything in R star, the result of taking the determinant of A. So the claim is this is a group homomorphism, and very interestingly, the kernel of this homomorphism is nothing more than the special linear group itself. That's the claim. Okay, I see a lot of chats here. I forgot to check actually.
Claudia joined.
Okay, yeah.
I would just give a little hint that if this is true, that it's the kernel, then it would also follow that it's normal.
Okay, thank you. If you agree with George, you will be able to solve the next challenge. So the next challenge is exactly the corollary, as George is saying, rightly so. This is indeed, as a next proposition, as there you go. This is trivial to prove, as George just, made it clear. So this is indeed is a normal subgroup of the general linear group. Okay. Now this is this challenge 3. I hope I'm labeling the challenges correctly. If not, I will correct the slides, obviously. Whether this quotient here, because obviously if this is a normal subgroup, obviously we are allowed to take the quotient, right? Remember we did this in the abstract definition of a quotient, right? When we have a normal subgroup, we took the quotient. The challenge is whether this quotient is isomorphic to R star, so the multiplicative group of the reals. This is a challenge. What's the hint, George? Any hint whether this is true? Anyone else?
I'm trying to think of a hint just based on what we know. I've kind of got a more general approach, thinking of it as a projection.
Anyone has any feeling that this is true? Yeah, it's okay. You can think about it in the study sessions at home or on Discord. Okay, but the important thing, this question makes sense. Yeah, this is a valid construction because this is you just proved this is a normal subgroup. The question is whether there is an isomorphism between this quotient and this. So you have to, if you don't remember what a quotient group is, you have to go back, when we cover this, was it three sessions ago or something, or 2 sessions ago, something like that. Okay, I hope I haven't made any typos somewhere. Dimitri and the rest, George yourself, feel free if you spotted anything, because I was rushing to do the slides, so naturally there might be something off, maybe stating something that I meant something else. Okay, so another proposition, I could have used definition. I actually prefer to say, put this as a proposition so people can try to prove it, right? So we will now define this set to be the set, essentially the set of all orthogonal matrices. Okay, orthogonal matrices are the ones, linear algebra 101, the ones that satisfy this property. The claim is that this is a subgroup of the general linear group. Okay, so this is known as the orthogonal group. It's the group of all orthogonal n by n real matrices, and we'll take the convention for us to use O of n to denote it. This is typically what in the test books people do. They don't use this notation, so we will switch to that. I could have also obviously started doing it, but I thought it much more natural to start this way and then go through this, because some books still use this notation. So, but we'll stick with this one. So this is essentially, if you are more of a, if you're, taking the linear algebra, mix up with calculus and these things, you will, analytical geometry and all this stuff, you will know this is actually, in essence, this is the group of linear isometries on Rn. So the linear maps that preserve, distances between points on in Rn. Okay, and so they preserve the length of the vectors in Rn. Okay, now this is very tricky. I think you will recall that there are isometries that are not necessarily linear, and so O of n cannot include all the possible isometries. Okay, so it only contains the linear ones. Okay, so I hope this is just a call of precaution there. Any comment, George?
Yeah, I'm maybe jumping ahead again, but I would relate isometries to the inner product.
Yeah, as well. So it preserves. Yeah, correct. Yeah. Correct. Another nice fact about this is actually, when it is the symmetry group for n-1 sphere. So this is the group, the symmetry group for it. So for example, O of 3 is then the symmetry group of the ordinary sphere, and O of 2 is the symmetry group of the ordinary circle. Okay, and again, just to give you a motivation, there's some line here, I don't know why. Just to give you a motivation is that connection with the Lie group. This is actually the other two examples we have seen so far were non-compact Lie groups, but this one is a compact Lie group, and the dimension of it is this thing here. If you compute it again in the Lie group section, you will learn how why this the dimension is this thing. You cannot do that. We need topology and differential geometry to get to that conclusion. This is not just algebraic stuff. So, okay. And now we go to the special orthogonal group. So they are coming in fast. So we have orthogonal group, and we are now interested in a narrow in a special type of orthogonal groups, namely the ones, namely the members of the orthogonal group that have determinant 1. Okay, so the claim is this is a subgroup of the orthogonal group itself. So all the elements of the matrices, the orthogonal matrices that have determinant 1, they form a subgroup. So therefore, they're a group as well. That's why it's called the orthogonal. This is actually the real special orthogonal group. Okay, like in the analog of with the special linear group. Yeah. In fact, I didn't mention this. You can obviously see this is an intersection between the orthogonal group and the special linear group, right? Because it has to have determinant 1, right? So this is, you can view, this is the group of rotations on Rn. And as a side note, this is also, I claim this is also a compact Lie group of dimension, the same this dimension here. I hope I didn't make typo. If I made, you will be able to correct me on the thing on the Lie group section. And here's another proposition. That's why I decided to use proposition instead of definition, because to encourage you to try to verify that these things are a group. And now this one. George, you were saying something? I hear the microphone. Did you find?
I've got to think about the dimension a bit.
Okay. Have I made a typo? Should this be something else? That's the question. Yeah.
Yeah. Yeah, I'm not sure if it's a typo, but it's also more likely that I'm a misunderstanding.
Yeah, no, that's fine. You can ping actually on the thing on Discord if you think this is a thing. Obviously, this is not this is the dimension. This thing of this is just out of scope of this abstract group theory thing. But obviously, I'm happy if you go and figure it out yourself whether I made a typo or not, and then let me know on Discord, and then I will confirm with you.
No, I think it's not. I think it's right upon thinking about it. I think n times n minus 1 divided by 2 is right. Yeah.
Okay. So we will come back to this in a thing. We will be able, for those of you watching on YouTube now or online, if you're not understand, this is just a side. That's why I put it as a side note. You don't need to know this now. You will know this in the thing in the context of Lie groups. We'll revisit manifolds and all this stuff, because that's where this is coming from. So here's another proposition. Proposition 1.5. There's a lot of them. So let R star again be the multiplicative group of the non-zero real numbers, okay? And let's take the determinant again, but let's restrict it to the orthogonal group, okay? The claim is that this is also a homomorphism, and the kernel of it is nothing more than the special orthogonal group, okay? So as a corollary of this, then this is saying that obviously the special orthogonal group is a normal subgroup of the orthogonal group. Okay. To see this, obviously you need to remember the isomorphism theorems for we went through in a couple sessions ago, group isomorphism theorems, right? The kernel of a homomorphism is a normal subgroup of the domain group. Okay. So this is where it's trivial also to prove because the kernel of this is a homomorphism, so you need to prove that this is a homomorphism, and it follows then because we are staying here that this is the I think it's easy to see here, because the unit here is 1, right? The identity, right? So yeah. Let's go to the next, which is a series of challenges. So the first one is what I call isomorphism question 1. Which of the following is true, if any? So option 1 is this quotient isomorphic to R star, so the multiplicative group of the reals. Is it isomorphic to this group, where this is like the multiplicative group, and of this set under the ordinary multiplication of the reals? Okay, and is it isomorphic to this Z2, where Z2 is the group under mod 2 addition? Yeah. So which one is, if any? It could be maybe all of them are. This is not true for all of them. There's no.
It can't be all 3.
Yeah. Yeah. Is that the case?
Unless Z2 is isomorphic to R star plus.
Well, that's the question.
Yeah.
If any. So it could be just one. It could be maybe, one will lead to the other.
Okay. Well, I need to think about this one. So these are some serious challenges this time.
Yeah, and just as a hint, obviously these guys, for example, these are finite groups, right? So so you can think, if you can build an isomorphism from here, for instance, can you build another one from here and here? Yeah. Anyway, this is just the thing, an extra thing to maybe confuse you, to throw you out of thinking, or maybe not, or maybe give some useful thing to go and think about. Yeah. So the second question is this abelian, I call it abelian question, is whether the special orthogonal group for the case of n equals 2, so SO of 2 is abelian. Okay. And then the other question is, what about for the case n equals 3, and even better for the case n greater than 2 in generality. Okay. And this is a hint for the case of n equals 2. I hope I didn't make any typo here. So this is in principle, if I didn't make typo, this is the form. The elements of this can be written in this form. Okay. So all you have to do, obviously, is to go and multiply two elements of this form and see in different orders and see if they commute. If they do, then it means this indeed is true. It's abelian for the case of n equals 2. And the final challenge is the isomorphism question 2. So consider this multiplicative group. Let's call it the circle group. Okay, this is the group of all complex numbers with the absolute value 1, with modulus 1. So the question is, under multiplication, the question is if this is isomorphic to the special orthogonal group with n equals 2, SO of 2. So this is the thing. Any hint here?
I think the previous challenge gives a big hint.
Okay. So this is it. Yeah, go ahead.
Or just how you can represent the complex numbers would be another hint.
Yeah. I actually wanted to give some extra hint, like the thing with precise mapping from S1, from SO2 to S1, for example. Asked whether that was an isomorphism, but then I was running out of time. I decided to ask the question this way. Yeah. So this is it. In terms of in the next session, I will see if I can briefly mention other interesting matrix groups, like symplectic groups, for example. Let's see. But then I also want to touch a bit about, this is a question also, maybe I should ask here, how do you prefer to do this? Do we jump straight into complex matrix groups, and then and the thing after that, after we go all through the subgroups of the general linear group, just like we did here, we then have the rest of it about representation theory? Or in the next session, I can start with a bit of representation theory for the real case, so representation theory over real vector spaces, and then we move on to complex matrix groups, and then we do the same again after we go through the subgroup stuff of the general linear group over a complex field. We define representations over complex vector spaces. So what do you prefer, George?
I'm prepared to jump ahead, but I may be more comfortable with the geometry and thus with the real case. If people are less comfortable with the geometry and topology, they might need to work harder on the challenges.
Okay.
But for myself, I feel comfortable with all this stuff. Any difficulties are not deep. It's just, lapses of mental typos.
Yeah. Okay.
More quiet on the chat.
Is it the case for everyone else on the thing? Yeah. Okay.
Dimitri agrees.
Okay.
I had also one last question, although it might be moot, is how the survey went on the time.
Yeah. I will share that in a minute. That's a good question,
Okay.
actually. Let me actually pull it. I forgot to mention it. I was meant to mention it in the thing at the beginning of the session. I knew, yeah. So let me pull it. I think mostly the regulars who had the thing to answer, and vast majority want to keep it the bi-weekly.
Okay.
As it is, yeah. Because I guess it's only like maybe like 2 weeks difference anyway. So
Yeah.
it's not.
And I'm also thinking that for those of us in America, there'll be a Thanksgiving week.
Yeah.
I mean, Thanksgiving on a Thursday right before, but
yeah.
the people are too full.
I actually forgot about it. Yeah.
If some people are then too full of turkey on Friday to think clearly.
Yeah. Yeah, I forgot about it. Yeah, so maybe that's why people, the vast majority. I'll just stop recording and then I will go through it. Yeah, so for the ones watching on YouTube, before I discuss the survey stuff with the rest on the live audience, the session, the slides provided nobody finds a typo and makes me alert, alerts me about it. I will upload this as soon as possible, and the video will also be available on YouTube as soon as possible. So yeah, so feel free to join the Discord, and engage with other channels, with the other course like the functional analysis and the measure theory course, for instance. So yeah, so thank you for being with us in this journey. So I will stop recording and I'll see you in the next session.